Okay, greetings to everyone. In today's class, we will be discussing about the continuation of the deformable image registration models. So in the previous class, what we were discussing about was how the barycentric interpolation can be used to find the value of a point which is present inside the triangle, which is formed by 3 pixel intensity values, let's say x1, x2 and x3. And what is done is basically a weighted averaging of all these pixel intensity values, and the weights are determined by the ratio of the areas which are formed or under each of these points over here, right? Now, next in today's class, what we will be discussing is about the AAM or the active appearance model. So this is basically abbreviated as the AAM model. So what we'll see is how this barycentric interpolation technique can be used for deforming a given object, okay, with respect to a reference frame. So let's say you do have an object which is given to us, okay, along with some landmark points, and we need to deform this object to get some desired output. Now that desired output can vary. So if you are deforming this object over here accordingly, it would be based on a certain relaxed points, okay, in the sense certain points to which, or the target points to which this would be deformed. And once the deformation is done, you get the output of the deformed image. Okay, so we'll see the details of how it is done. So in this particular figure, if you see this figure, this reference points image that you see here is basically the image that we consider as S, or the source. And the relaxed points image is basically my target image, right? So as we already know, what we do is in the source and the target images, they have deformable objects, okay, which in the sense, this is a deformable object, or the object that has to be changed, right? So what has to be changed now? In this image, what you see is basically a person who is smiling, and my in this example, my target is that I need a person who is not smiling, or in the sense has got a relaxed emotion or expression on the face. So as you see over this particular image that is seen here, okay. So now what we do is, or what we are assuming is that now this is the source set that I have, and this is the target set that I have, right? So I am assuming that I can deform this image to this, okay, if I can find out what is the transformation which is required. Now there would be there exists a transformation between the source and the target images, right? So if I transform this image with respect to the target image, I can get the deformed image, right? So what we do here is we are applying the transformation, as I said earlier, and when we are doing the transformation, right, apart from the shape which is present, right, I'm also considering the texture which is present, or the appearance of the images also. So even though the relaxed points, or the target, it shows just the landmark points over here, that is basically the shape, okay. Accordingly, when you're doing the transformation, you also take into account the different texture regions, or the appearance also. Now, as I just right. So because you take texture as an important component, right, that is why it's called as an appearance model, because it takes into account the texture. And this is basically a very popular algorithm which was developed in 2001 by Coates et al. And this particular model, it is mainly applied to the face images, where face images of different expressions or emotions can be generated. And but Apart from that, it has also been used, the AAM or the active appearance model has also been used for various other applications also. It has been used for medical applications for deforming bones, etc. Okay, so it does find various other applications, but it started off with, the face images, and it's more popularly, worked with on face images. Now, here, what we see is that now these landmark, you see these landmark points over here, right? So each set of 3 points, as discussed in the previous class, you can assume that each set of these points can form a triangle. So I can form a triangle over here. I can form another triangle with these three. I can form another triangle with these three, and so on, right? So I can kind of form a triangular mesh with all the landmarks which are present over here, right? And these reference points that you see here, they assume to be, having a fixed location throughout, okay? Now, in order to deform this space so as to get a relaxed expression, okay, what we do is we make use of the barycentric interpolation that was discussed earlier. That is, if I know what are the pixel intensity values of these 3 points over here, then I can find out the corresponding, I can interpolate and find out what is the value of any pixel which is present inside here, okay? So while I'm trying to deform the image, right, I have the old or the actual set of landmark points. I also have the target landmark points. So when I'm trying to move to the target landmark point, that target landmark point would be the new pixel intensity which I have to find out, and which would be present inside a triangle, right? So that is how we make use of the barycentric approach. We were discussing in this figure, right? So these relaxed points are the landmarks that you have, right? And what we do is, given this reference image along with these landmark points over here, right? The target image, okay, we want is basically a person who is not smiling, right? So for this, what we do is we have a set of points which are called as the relaxed points, okay, as we see in this figure. Okay, and this relaxed points, or basically the target set, is the reference for which the person is not smiling. Okay, so this we consider as the framework for a person who is not smiling, and then we are trying to deform this image with respect to these relaxed points over here, right? So that means what we do is we basically apply the barycentric interpolation approach, right, between these two images, or the reference points as well as the relaxed points, and therefore we can find out what is the intensity value of each of these relaxed points by making use of the barycentric interpolation approach. Okay, so let us see what are the mathematical details for this particular problem statement, or this particular algorithm. Okay, so here we can write, given a point P which you have to find out, right? So we can write it as SB1 plus TB2 plus 1 minus S minus T into V3. Okay, so what this means is, see, V1, V2, and V3, okay, they are the vertices of the triangle, right? And what we are trying to find out is, in this triangle, I have a point, right, which is given by ST, okay, and I want to find out what is the value of a point which is present inside. So I can write it as P is equal to, now these are basically again a weighted averaging itself, right? But here the weights now are represented in a different form, that's all. But basically these ratio of the areas itself, okay? So by using these different weights, what you can do is you can try to interpolate and find out what is the weighted average, okay? So it is the same as before, it's just that the notations have changed over here. Okay, now here this I naught. So if the original image that we are considering, right, if we can assume that to be I naught, yes, then the reference intensity value which you're looking for can be represented as I naught of P of STV. Okay. So next what we do is, okay, so given this original image with the pixel intensity values, Okay, what we want to do is we want to map these I naught, okay, to the new target image, which can be represented by, say, in, right? So we can think of this mapping over here as though you're trying to deform the original triangle, okay, to get a new triangle, or rather, just interpolating. Like for example, let's say if I have I naught, this is the triangle which corresponds to the input. I can call it as the input triangular mesh. Okay. Then what I'm doing is basically what the problem is mapping this with another triangle over here. Okay, which is given by in. Okay, which is basically my deformed triangular mesh. Okay, so what that means is this in represents the target and I naught represents the actual image. Okay, so from here what I'm trying to do is I'm trying to kind of map or deform this in such a way that it forms this in or the new deformed triangular mesh, as you see over here. Okay, so when we are trying to deform this point by point or landmark by landmark, what we are doing is we are essentially deforming the whole object, okay, along with the texture information or the appearance of the object. So if you look at this particular figure, what we'll see is these are some examples of the different images that can be created with this kind of an approach. Okay, so for each of these images, what is done is it has got a different set of relaxed points, okay, or the target set that you have is different for each of the emotions. Okay, so using the same input image, let's say I naught is the input image that you have, using the same input image but different relaxed points or different target set, okay, what happens is you can create different emotions as seen in this particular figure. So this is one use of the active appearance model and how the weighted averaging or the barycentric interpolation can be used for deforming the objects. Okay, so as discussed earlier again, the main application of the image registration is basically in the medical imaging system, okay, or the medical imaging field. So in medical images, we know that there is something that we are looking for, okay, and but we need to find out where exactly it is. Okay, so it's like we know that there is some kind of a diagnosis, okay, which may be present or which may be causing the symptoms, but we need to find out where exactly it is. If you know where exactly it is, you also would need to find out what is the area or what is the shape or some other maybe texture information, etc. Okay, all of that when it comes to diagnosis. So there are various applications of how we can or how the image registration is helpful in different applications in the medical field. So one such example is, let's say you are having some follow up. Okay, like for example, let's say you have taken the scan of a patient. Okay, if the patient has visited the clinic today, and you let's say the patient has got some kind of a tumor growth or so. Okay, now the doctor wants to monitor if the tumor is growing, okay, or how much it is growing, or such kind of details about the growth of the tumor. So what happens is the doctor may call back the patient after a week or maybe after a month or so, and then again scan the patient once again. So each time the same patient has been scanned in order to see what is the growth or how much it can be growth, sometimes it can be reduction also. Okay, so in order to anyway monitor what is the size of a particular disease condition in the same patient, it may be necessary to have some follow up studies, okay, or follow up scans. So what happens is when you're having such scans, okay, you need to register the scans together, okay, because basically it's from the same patient, it's about the same organ, and what we are trying to identify is what is the growth over there, right? So first you have to go with the image registration, okay. Register all the images together before you go about trying to find out what is the size of the tumor, or trying to find out any other underlying information or details, if there are any. So that is one example where you have these longitudinal studies or follow-up procedures, okay. And another example that you can have is regarding using multiple modalities. So sometimes you may be dealing with multiple modalities, in the sense the image of the same human organ, okay, can be captured by different images. So by capturing such different images of the same organ, what we are trying to do is we are trying to find out more details about that particular human organ, right? So in that case also you need image registration, because you're looking at the same human organ which is of the same patient and which has been taken around the same time, and you want to find out more subtle details, and in order to do that you need to register the images together to get a combined information, okay. So like that, there are various applications for the medical imaging field. So what you can say is that each time you're dealing with such kind of image registration, in the medical field, uh, it would be difficult for each scan you are taking. It may be difficult for maintaining the patient to be at the exact position, exactly as it is, or exactly as how he had taken in the previous scan, okay. Or that would be a very difficult task to do, okay. So what is useful over here is to do the image registration to align both of these images together. So always there will be some kind of transformation that may have been occurring between these two images. So if these two images of the same patient, of the same human organ is different, then that means you can say that there is some transformation that exists between them. That is, if I apply this transformation to this image, I should be able to get this image, right? So I have that assumption, and then I try to align the images together before I go further with further processing of the images or further diagnosis, etc. Okay, so let's say, so as I told earlier, right, we can have different imaging modalities that can be used for capturing the details of the same human organ, okay. Like for example, I can take the MRI scan or CT scan of the human brain, and then I can try to superimpose them together, okay. And I can also project it onto the actual patient also, so that I can help with the surgical planning. So that can also be done, okay. So another example that you have is the pose estimation, okay, which is shown over here, right? So as we see over here, what we see is a particular slice of the MRI scan. So as we know, MRI scan it has got different slices. So this is just one particular slice from a particular view of the MRI scan, okay. And you can see that there are some green, yellow, and red boundaries which are shown over here, right? So these are different regions of interest which are present in the patient's brain, right? So given this particular segmentation, as you see over here, right, we can superimpose all these regions on it, okay, while the surgery is going on, okay. So like for example, okay, so let's say you have a patient which is being scanned, right? So when the surgical procedure is going on, right, these scanned images, they can be registered together, and then certain regions of interest are segmented from the registered images, and that can be projected on the patient itself, okay. So basically in such a case what happens is that the image that you have taken, the MRI image which was shown earlier, that is basically a 2D image, right? All the segmented regions, that was basically a 2D image. And here, when you're projecting it onto a patient, means basically what you're doing is you're superimposing to a 3D object, right? So that means here the kind of registration that is happening is a 2D to 3D registration, where you have the MRI scan of the brain and you have segmented the regions over there and you're trying to superimpose that. So it is basically a 2D to 3D transformation. Okay, and this is one example of that. Okay, where you see that these segmented regions have been projected onto the patient. Now, why it is important is it can help with surgical planning, as well as before the surgery, as well as also during the surgery for the surgeons, because let's say they are working with some needle hole surgery or so, it will help them to identify whether they are going at the right region. Okay, and it can help with guiding throughout the surgery of the patient. So this such kind of techniques exist, and for these techniques that you're using, the image registration would play a very important role, and that's why it's important that we learn about these two. Okay. So, as we said earlier, right, what we are doing here in the medical image registration field, basically what you're working with is the human organs, which are not rigid. Okay, in the sense these are deformable objects. Okay, it changes during time. So each time you're taking an image, the organs tend to change the shape, or okay, or slightly the location, etc. And so one reason is again that the organs, they are not rigid, and they may they may deform during the process. Another is that there might be motion of the patient also. The patient movement can also cause changes in the images, right? So what we see is that in medical images, it is very hard to to get an actual exact images which are exactly aligned with each other. Okay, and therefore whatever images which are taken in different modalities, if you are working with either different modalities or within the same modality also, if you're working with different images of the same patient or the organ, okay, or for the same purpose, then definitely image registration has to be done. So in the medical field, remember, in all medical applications, the image registration plays a very important role, and especially the deformable image registration, because as I said, okay, both the human organs as well as the patient during the image acquisition, it tends to change the position, and so it is important to register or align them together before we go further with further processing. Okay, so here what we see is an example of a human organ, okay, in which there is some contrast agent. So here this arrow mark over here, okay, it shows that there is some kind of a contrast agent which is present over here. Okay, and what is done is in this example, the contrast agent moves. Okay, and we're trying to see how much or what is the movement of the contrast, or what is the how much it has moved or spread or so on. Okay, so what we are doing is, first you have the image taken with the contrast agent. Okay, and you have another image that has been taken, okay, after the contrast has moved, okay, or the contrast agent has moved. And what you're trying to do is, we want to try to find out what is the difference between these two images, because the changes in the contrast agent or the movement of the contrast agent would give us more information of what we are looking for, the diagnosis that we are looking for, or which the doctors are looking for, right? And so if you want to find out the difference of these two, Okay, there are different ways by which you can do that. Okay, like for example, you can just take these two images, and when you look at it, okay, it kind of looks, somewhat similar, or somewhat which is aligned together, but it is not. It's clearly visible that it's not. Just look at the distance over here, right? So let's say, it visually looks that it has been aligned together, and if you simply do a subtraction of these two images, okay, in order to find where exactly is the contrast agent. So without doing any registration, if you're simply finding the difference between these two images, what happens is, for example, you see these kind of a false edges which is formed over here. Okay, so basically what this is these two images, they are not aligned together, and because they are not aligned together, you see these information over here, okay, which is basically of no interest to us, because what we are looking for is for this particular change in the contrast agent. Okay, so in order to avoid that, okay, it is important that we do the image registration. So let's say we are doing some kind of an image registration. For different image registration, depending upon what is the transformation that you have used, the results or the difference images will show different results. Okay, like for example, let me say that I have used the rigid registration. So if I have used a rigid registration, okay, that means I took the original image and I have image one, okay, basically, and I have image two, or let's say this is the source image, and this one over here is the target image, and let's say I have registered them together using the rigid registration. So after the rigid registration, when I take the difference, okay, over here I see that I do get where exactly is the contrast agent movement, but still I do have some white boundaries which are present over here. Okay, so again, what that means is a rigid registration, though it does show where exactly is the contrast agent, but still it is not as what I say, it still has some errors because the alignment or the registration has not been perfect. Okay, so what can be done is, so that means rigid registration usually means it's just a translation or a rotation over here, right? So just by translation and rotation, we really cannot, align medical images together. Okay. Now we can try with an affine transformation, which also includes a linear stretching. Okay, and you can see this is the result over here. And you also have deformation. Registration or deformable registration which can be done. Okay, so the difference over here is that in the deformable registrations that is being applied, you assume that the objects which are being imaged, okay, gets deformed over time. So when you use such methods where it takes into consideration these deformable objects, what we see is, as you see in this figure, okay, it shows much better results than that of the affine as well as the rigid. Okay, and the contrast agent also shows, you're able to clearly identify where exactly is the contrast agents, but at the same time, all these boundaries, the white boundaries or the false edges that has come over here has kind of reduced. Okay, so in medical image processing or the imaging, what is important is making use of the deformable image registration, because as I said, the human organs, they are deformable and not rigid objects. So there is a difference between the medical imaging or the image registration and the rigid registration techniques which we had studied earlier, right? So in the earlier registration techniques, as we said, okay, only the individual pixel values were considered. Okay, so that means we were trying to compute what is the transformation which was present between the individual image pixel values, okay, which is present in the source as well as the target. Okay, but when it comes to medical images, the thing is we cannot we cannot exactly use these kind of pixel to pixel dependent registration techniques. Okay, like for example, let's say I have an MRI image of a brain and I have a CT scan of a brain. Okay, so when I consider these MRI scan as well as the CT scan of the same object, let me assume that it's a brain. What we see is we cannot exactly take a pixel to pixel comparison over here. The reason being, the pixel or the intensity that we are considering over here, okay, is taken from another modality. And here the pixel intensity which we are taking is again from another modality. So because it is from another, different modalities, what happens is the exact pixel values, okay, would not be the same. So when you're trying to kind of register different imaging modalities using this pixel values, it becomes difficult, right? So we cannot, what happens is we will get different pixel intensities for the same region in both the MRI and the CT scan, and so therefore that cannot be used. A pixel to pixel value comparison cannot be used for registration of the medical images. So here what we can do is we can go about by finding out what exactly is the imaging modalities which can be used. That is one approach. One approach that you can use is basically create a lookup table where you know that, okay, I have an MRI image and I have a CT scan, and this is, I have a pixel over here, okay, or I have a set of pixel values. Let's say for the MRI, I have a set of pixel values that which are possible, and for the CT scan, I do have that, and I can kind of map that. Okay, if this is the pixel intensity, the corresponding pixel intensity is here. If this is the one, the corresponding one is here, and so on. Such kind of a lookup table could be used for such kind of a mapping between pixels to pixels, okay, but again it has got its own kind of limitations over there, okay. So it does not really give us the best results what we are looking for when you're using a lookup table, okay. Because even if you're considering the same modality now, that is, for example, even if it is, if I'm not using a CT scan and if I'm using MRI itself, even within the same modality there are different types of MRI scans, like you have different kinds of T1 weighted or T2 weighted or so on, different kinds of contrast and without contrast, etc. So within the same modality itself you can have different kind of images. So going about with a pixel to pixel direct conversion is not very practical when it comes to clinical applications, okay. So what we do is a better approach which is used is basically called as using the mutual information, okay. So rather than looking at the pixel intensity values, we try to find out how much is the mutual information or how much is the information which is present between the two images, X and Y. So we'll have a look at what exactly is the mathematical formulation for this, okay. So let's say I'm taking two image modalities of the same organ. So I have a human brain here, I have another human brain, I mean the same patient, the same organ, but another image of the human brain, okay. And this is basically the CT scan and this is the MRI scan. So what I'm trying to do is I'm trying to kind of find out what is the mutual information which is present here. So in order to try to understand that, we need to also understand what is basically a joint histogram, okay. So what I'm doing is so let's say I have two images, okay, of the same organ which I'm considering. Let's say for this example, if it's a brain, let's say I have two images and it is the same organ, okay, and let's say it's exactly the same. You're taking exactly the same image. So if you're taking exactly the same image, the kind of transformation I have is an identity matrix, okay, because this is exactly the same to each other. So it would be basically a identity matrix. Now, if you know what is the transformation between these two images, that is to this image, if I apply the particular transformation, I get this particular image, right? So if I know what is the transformation over here, I can compute what is called as a joint histogram. So how I compute is the of the joint histogram is Okay, let's say the two images that I have is X and Y. So this represents image X, this represents image Y, and what I'm doing is I'll just plot the pixel intensity values along these axes. Okay, so I have 0 here, let's say 1 2 3, and this goes on. Here I have 0, again 0 corresponding to this, then I have 1 2, and then this goes on, right? So you have all these pixel intensity values which are plotted along the x-axis and the y-axis, okay, of this joint histogram representation over here. Now what I do is, for each of these pixel pairs, I try to find out how many times, okay, the pixel pairs or the pixel intensities occur together. That means if I take this particular first element, okay, it will show me how many times 0 and 0 has occurred together, okay, in X and Y. Okay, so I kind of do a pixel to pixel comparison over here, and I also look at the pixel intensity values, and I try to see how many times they have co-occurred together. Okay, so for example, let's say if you're counting and you get some number, let's say 4, for example, you get let's say 4 or 1 or maybe 2, and let's say 8 or so on. Okay, so you can get kind of different numbers over here, right? So what I'm doing is I'm trying to find out, okay, how many times. So I have combinations of 0 0 0 1 0 2 0 3, again 1 0 1 1, and so on. For all these combinations, I can find out how many times all these pixel pairs occur together. Okay, now now having done that, let's say if the transformation that you have is an identity matrix. If it's an identity matrix, what we'll observe is you will have non-zero values only along the diagonal over here. That is, for 0 0 I have a non-zero number. For 1 1, along 1 1 I'll have a non-zero number, and so on. And for all the others I'll have zeros. Okay, so this case exists if I'm using an, or if the two images are exactly the same, right? So if the two images which I am considering are exactly the same, right, and I assume exactly the same in the sense it is an identity transformation, okay, which has occurred between the two images, then if I try to calculate what is the joint histogram, what I see is there will be non-zero values which are concentrated only along the diagonal of this particular axis when you're trying to plot the pixel intensity values of X and Y images. And in all the remaining elements, you'll have it as 0. So that means if these two images are perfectly aligned with each other. But if they are not aligned with each other, then that means that you will get some non-zero values in the other areas also. So this how many non-zero values, or through how much the non-zero values are deviated, or how much it is present along the diagonal, okay, concentrated along the diagonal or deviated from the diagonal, will tell us how much of transformation is present. Okay, so if you have some kind of a transformation, okay, which is just a very small transformation, then you might see that let's say the transformation which I'm assuming is some kind of a rotation. So if it is a rotation by a small degree, you find that you'll have less number of non-zero values which have been deviated from the diagonal. Okay, if you are increasing the rotation to a higher order or degree, what happens is there is more of a misalignment between both images, right? So you'll see that the non-zero values would be spread apart from the diagonal. Okay, so an example is shown over here. So in this particular figure, what is seen is if it is 0 degrees, okay, 0 degrees in the sense the two images that I'm considering are basically identical images and they are exactly the same. So in that case, what I see is in the joint histogram, Okay, you see that all the non-zero values are exactly along the diagonal, but if I'm trying to increase the degrees of rotation, I see that there are non-zero values which are present along the diagonal, which are spread or deviated from the diagonal. For 5 degrees, again, it is deviated more, and for 10 degrees, you see that it has deviated even further. Okay, so by looking at the joint histogram over here, we can tell how much of deviation or how much of transformation has occurred between the different images. So let's now just have a look at the mathematical formulation of the mutual information. So when I'm looking at mutual information, okay, so the joint histogram which we were discussing about is basically this one, that is P of xy represents the joint probability, okay, of the two images. Okay, this stands for image x and this is for image y, and this is the joint probability of the two images. Okay, so and this is a denotation for the mutual information. So this same mutual information can also be expressed in terms of the entropy. That means I can say it is the when you're trying to add the entropy of image x with entropy of image y, and from that you're subtracting the mutual entropy of the images x and y. Okay, that gives me the mutual information. So what I say is that if the mutual entropy which is present between the images, if that is less or if that is decreasing, okay, or if that is minimum, what happens is the mutual information which is present is also that is maximum, right? So it has kind of a what inverse approach over here. So what we're doing is, or how we are formulating the mutual information is, we write mutual information is equal to the entropy of the of one image plus the entropy of the other image, and from that you're subtracting the mutual entropy between both the images. And then what we do is we use it as a maximizing problem over here. Okay, so we try to maximize the mutual information which is present between both the images. Okay, so let's have a look at this example here. Okay, so in this particular example, you see that these two are images, okay, of different modalities, but of the same object. The underlying object is the same for both of these, okay. So you see that if you're looking at a pixel to pixel, if you're just simply comparing pixel to pixel intensity value, it's going to give us a very wrong result over here, right? But when you're looking at these two images, you know that it is of the same object that is seen over here. Okay, now when I'm trying to do, or when I'm trying to find out the mutual information of these two images, okay, what I basically do is I try to try to find the entropy of each of the individual images, and then try to subtract the mutual entropy between the two images, right? And let's see how the results would look like. So let's say that I'm considering this particular point over here, P, okay, and here there are 2 points which has been considered, which is point A and point B. So when you look at this figure, you know that this particular point P, okay, the corresponding matching point in this particular image is basically A, right? So when I'm calculating the mutual information, okay, between these two images, what I say is, at the point A, okay, corresponding to point P over here, at the point A, I see that there is a maximum value for the mutual information. Okay, and if I consider any other points, let's say B over here, I see that the mutual information has reduced. So for all other points other than A, the mutual information is reduced. Okay, but at the point A, this mutual information peaks. So by looking at the peak of this mutual information plot, I can say that, okay, this point over here, A, is the matching point for point B. Okay, so how mutual information helps is, it helps us to identify, okay, which is the point which is which is matching to the point that we have been considering over here, or which is the matching pair of points that you have. Or basically it tells us how much is the probability that the 2 points that we are considering has come from the same source, okay, or from the same distribution. So by looking at that, so here it gives a high value, means that it is very highly probable that these 2 points come from the same source, okay, or come from the same kind of model that we are looking at, okay. So by saying that, what happens is, now since now mutual information is kind of a probabilistic calculation, right, where you're not exactly looking at the point to point pixel intensity values directly, okay, it will work irrespective of what is the illumination variation which is present in the two images, okay. That means even if I use two different modalities of the same object where the illumination is basically different for both of those images, still the mutual information will work, because it does not work directly on the pixel intensity values, and that is one very good main advantage of using the mutual information. Okay, so next we'll see what are the different classification, or how we can categorize different registration methods. Okay, so the different ways by which we can classify the registration methods. There are different categories that you can create. Okay, so you can consider various parameters, like for example, we can consider the dimensionality, what is the registration basis, what is the transformation, etc., to categorize the different registration methods which are used. We'll just quickly discuss about each one of them. So the different 8 categories is, the first category is based on image dimensionality. Okay, we can try to classify registration methods. Okay, that means we can have a look at the image dimensionality, whether it's a 2D image or whether it's a 3D image that we are dealing with. Okay, we can try to categorize the registration methods as 2D registration methods or 3D registration methods, etc. Now, another category is based on the registration basis. So that means we can see whether it is a point-to-point, registration, or are you using frame bearing groups, etc. So depending upon what we are trying to match between the two images, okay, we can again try to categorize the registration methods. Then another category of registration methods, is based on the geometrical transformation. So what that means is, depending upon whether the transformation that you're using, whether it's a Euclidean transformation or whether it's an affine transformation, etc., depending upon what is the transformation that we are considering, again, you can classify different registration methods. Now, another set of, another parameter that can be used for categorizing the registration methods is the degree of interaction. Okay, degree of interaction in the sense, is it a fully automated registration method, or is it a semi-automated registration method? Okay, or does it involve any kind of a manual intervention, and so on. And another kind of category is the optimization procedure. Okay, that means what is the optimization algorithm that you're using, okay, for that particular registration method. Like for example, just in the previous case, we saw that we use a mutual information method, right? And what we are trying to do is we are trying to maximize the mutual information, right? So like that, for different approaches, registration approaches, there would be some kind of, either it would be maximizing a parameter or it might be minimizing a parameter. So depending upon what is the optimization method which is used, also you can try to categorize the registration methods. Then another parameter which can be used for categorization is the modalities. That is, whether the images which you are trying to register, are they, are they coming from the same modality, or are they coming from different modalities? So same modality in the sense, you call it as intra-model or mono-model. Okay, that means images which I'm considering, both may be, MRI and MRI, or both may be CT and CT, or so on. So if both the images come from the same modality, then I can call it as intra-model or a mono-model. Okay, or if it is, let's say, intermodal or multimodal, in the sense now I'm trying to register between MRI and a CT scan, for example. Okay, if I'm doing that, then you're actually trying to register two different modalities together, right? So such kind of a registration method can be called as an intermodal registration method, or you can call it as multimodal registration. Okay, so yet another category of image registration is the subject. Okay, depending upon what is the subject which is used. That is, if I'm considering two images, again the source and the target image. Okay, is the subject or the patient that I'm using for the the source and the target the same, or is it am I trying to register two images of different patients? Okay, so there may be a need where you might have to register the images of different patients, or sometimes it is the same patient, or so on. Okay, so you can call it as intra-subject registration if it is, if the images that you're considering comes from the same patient. If it is from different patients, you can call it as an inter-subject registration. And the final kind of category that you have is based on objects. That is, which is the organ that you are trying to scan or register. Is it the head, the liver, the vertebra, and so on? So depending upon the object or the region of which you are trying to register, you can also classify the registration methods. So to give you an idea, a very brief idea about the fact that there are various registration methods. So for each of these categories, you will have a certain set of registration methods, okay, which are popularly used and which are still being developed, okay. And as I said earlier, in medical images or medical image applications, the registration methods play a very important role, because whatever you're doing next, okay, whether it be a follow-up study where you're trying to find the growth of a particular organ or a tumor, or you're trying to find if it has reduced the size, or if there is any other changes, if you want to find out if there is some flow of the contrast agent that has been injected into the patient, etc. So whatever that you're trying to diagnose, or what you're trying to even predictions also, when you're trying to do in medical applications, it is very important that you do image registration. And the kind of image registration that you do for medical images, the effective ones are the deformable registrations, where you assume that the object tends to deform, okay, due to various reasons. And another type of registration which we had studied before that was the rigid registration, where it assumes that the objects that we are dealing with, or that we are considering, are basically rigid, okay, and there the registration methods become easier. So by this we end the topics on image registration, and from next lecture class we'll be discussing about the different techniques for tracking. Thank you.